Greetings, everyone. Today we're going to take a look at Unit 7 and review some of the key topics. Let's start off with exponents. If you would take some time to open your notes to our exponent rules table. We also had the orange sheet of paper that was very helpful in this process. Let's do a quick review. For the product rule, that means that if I have a to the n times a to the m power, that means I'm going to add the exponents and keep the base. So again, we're going to add the exponents. So for example, if I have x squared times x to the third, that would equal x to the fifth. Power of a power. What that means is if I have a base with a power to another power, I multiply those exponents. So we have to keep these two separate as far as when do I multiply and when do I add. It depends on how many bases you have. It depends if it's power to a power or if you're multiplying bases. So for example, if I have x squared to the third, I have x to the sixth. On a test, if you wrote down these quick examples up in the corner of a test, it'd be an easy way to remember the rules. Let's take a look at power of a product. What that means is if I was to have ab to the m power, I distribute that m to both variables. So a gets an m power and b gets an m power. So keyword here would be distribute. So an example we can take a look at. If I have 2x to the third, I distribute to both, which means 2 to the third and x to the third. And then I simplify one more step. 2 to the third is 8. So I have 8x to the third. Zero property. This is the easiest property to remember. What that means is a to the 0 equals 1. So anything with a 0 exponent makes the whole thing 1. So if I came up with something ridiculous, it doesn't even matter how many letters, how many exponents, if it's all to the 0 power, it's still just 1. Negative exponents. This is a tough one. This is one where we really have to take some time and make sure we remember the rules. If I have a to the negative n power, we kick it to the other side of the fraction. So pretending that there's an over 1 there, that means I kick it to the bottom side of that fraction, which leaves me with a 1 on top. So I'm going to really generalize this idea and say kick it. Kick it over. We're going to kick it over to the other side of the fraction bar. So an example could be, if I have x to the negative 3, it would be 1 over x cubed. If I have 2 to the negative 3, that does not make it a negative 2. You have to do the exponent rule first. That would give me 1 over 2 to the third, and then I'd simplify to 1/8. So you got to kick it first. Quotient property. I'm missing a little y there. Let's fix that. Quotient property means that if I have a to the m divided by a to the n, if I'm dividing like bases, I subtract their exponents. So keyword here is subtract. So for example, if I have x to the fourth over x to the fifth, that would be 4 minus 5, which is equal to negative 1. Well, now we got a negative, so let's kick it to the other side. That means I have 1 over x. Now, some of you know the shortcut. A lot of you know you can jump straight to the end by saying the 5 is larger, so we're going to keep the x on the bottom, and I do 5 minus 4, which gets me to 1. So that's a shortcut to skip a few steps. Power of a quotient means that if I have two variables, such as, let's say, a over b, and I have a power on the outside, I'm going to give this an exponent of m, this an exponent of n, and let's say an exponent of p. That means I distribute both the top and the bottom, and I'm going to multiply the exponents again. So very similar to the power of a product, if you take a look at those. So I'm going to distribute would be my keyword, right? So now I've got a to the m times p and b to the n times p. So an example could be if I have x over y squared all to the third power. I distribute top and bottom. That gives me x to the third. That gives me y to the sixth. Because I have a power to a power, I'm going to multiply those. So again, we have this table in our notes. We also have that orange sheet to help you out. If you need even more help, there's so many videos on YouTube about exponent rules or properties. So if you think hearing another teacher teach it would be helpful, then definitely pull up YouTube. Let's do one large exponents example. I'm just going to make one up here. I'm going to try to incorporate every rule that we have. Let's do that. There we go. Let's try this out. So I have many properties here. A lot of times it depends on what you see first. So in this case, I see parentheses first. So I'm going to distribute to everything, even the 2. This little 2 gets forgotten a lot. People are worried about the letters, but don't forget about the numbers. So that simplifies down to 2 squared. X to the 4th, because it's power to a power, so I'm going to multiply. Y squared, because technically that y has a 1, and z to the 6th. I haven't done anything to the bottom, so I'm going to leave it all in the bottom. Now some of you might notice that we've got y to the 0. Y to the 0 just becomes 1. 1 times anything is itself, so we really don't need to do anything further with that value. Let's take a look. Next, I'm going to take care of 2 squared, which is 4. I'm going to keep the 7. Now 4/7 doesn't reduce, but you have to keep an eye out for that. Let's look at our x's next. I have a quotient, so I'm going to subtract the exponents. The larger exponent's on bottom, so it's going to go on bottom. I have a 1 because 5 minus 4 is 1. There's only one y, so I'm going to leave it. Z. The larger z is on top, so I'm going to do z. 6 minus 2 is 4. Now really I don't need that exponent of 1. I could erase that because anything to the first power is itself. All right, let's take a look at one more example. If I gave you something that's not in quotients. All right, let's take a look. First thing I notice is I have parentheses, so I'm going to distribute into those parentheses. So every single piece gets that power to a power. So it'll end up being 2 squared, x squared. 2 times 2 is power of a power, so it's going to be y to the 4th, and then z squared. I'm going to leave that in parentheses for now. The second set, I'm going to distribute that cubed. So 2 times 3 is 6. Y, I've got 3 times 3 is 9. and z would be negative 12. Now, the fact that I have parentheses really is irrelevant at this point because I'm multiplying everything. So I can almost drop them and just take a look at what I have. So I'm actually going to change that to 4. Let's take care of that 2 squared. And I'm going to leave everything where it is, except for I've got a negative, and I'm going to kick that to the bottom right away. All right, let's take a look. I've got 2 x's. You should only ever have each variable once. So I'm multiplying bases, so I keep the base and I add the exponents. So 6 plus 2 gets me to 8. Take a look at the y's. I have 2 y's on top. I'm multiplying the bases, so I keep the base and I add the exponents. Let's take a look at the z's. I have one on top, one on bottom. The z is larger on bottom, so it's going to stay on bottom, which means if I take 12, subtract 2, I'd end up with z to the 10th. So in this case, that would be my final answer. All right, let's review scientific notation. So the basics of scientific notation is scientific notation is always going to have that times 10 with an exponent and a number out front. This number out front needs to always be between 1 and 10. It can't be 1 or 10. It's always going to be between those. So for example, you could have a 5. You could have a point or a 1.2. You could have decimals. And then your exponents could be anything. It could be positive numbers, it could be negative numbers. Typically, we don't see ones and zeros, but you're going to have another number there. So why do we have scientific notation? Remember, the mathematicians and scientists said, if I'm dealing with a very large number, I don't want to have to write this out every time I use it in a calculation. So we can convert that to scientific notation. To do that, we would have times 10. Currently, the decimal is here. I'm going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 places, which would get me to 3.2. 3.2 meets the requirement of being between 1 and 10. It's a positive 12 because it's a large number. Remember, when it's a very small number is when the exponent is negative. Let's take a look at a few more conversion options. So for example, if I gave you the small number of 0.000058276, and I want to convert that to scientific notation, I know I'm going to have times 10, and I'm going to have 2 numbers. Well, I need to move it. Let's count first. 1, 2, 3, 4, 5, 6 places. So I know I'm going to have a 6. I've got 5.8276. You have to write all of the digits. You only drop the zeros at the beginning or the end. All the other numbers stay. This 5 is between 1 and 10, so that's good to go. It's good. Now my 6, I have a very, very small number, so that's going to be a negative 6. Notice I counted to the right, so it was a negative exponent. Let's look at a very large number again. Again, no matter how many digits that I might have, let's say I have this very large number here, 32,678,100,000. I don't want to write that each time, so I'm going to convert it. This is going to be times 10. I know I'm going to have a number and a number. I know the decimal is going to end up here, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I moved 10 spots. So it's going to be a 10. Now I moved to the right, or excuse me, to the left. I moved to the left, so I have a positive 10. Because it's a very big number, it's positive. When it's a very small number, is often when we have a negative exponent. Now my new number is 3.26781. You do need all of those digits. Again, you only drop the zeros at the beginning or the end. Let's talk about multiplying and dividing scientific notation. What I mean by that is if I give you two terms in scientific notation, let's say I have a 2 times 10 to the 5th, and I have a -3 times 10 to the -2. If you take a look at this in general, really what I have here is 4 things being multiplied. So I'm going to take care of the items that are easy to multiply together. A 2 times a -3 is a -6. And then I have like bases. So when I multiply like bases, I keep the base, which means I add the exponents. So 5 plus -2. So that would give me a positive 3. We still need that times in the middle, so -6 times 10 to the 3rd. All right, let's take a look at a dividing one. Let's say I end up with, I'm going to just make one up here. I'm going to say 22 times 10 to the 5th. Oh, wait, I can't have 22. I'm going to do 2.2. And I divide by, let's say 1.1 times 10 to the 7th. Let's do something like that. So same thing, I'm dividing terms, so I'm going to divide terms that are similar. So I'm going to take the numbers out front and divide those first, whatever you might get. So in this case, I get 2. You're still going to have times. Here, I'm dividing like bases. So when I do that, I keep the base and I subtract the exponents. So if I do that, I end up with a -2. Now, scientific notation is the one case where negative exponents are okay in scientific notation because that's indicating I have a very small number. Okay. Now, occasionally, you might end up with a value that doesn't fit in the scientific notation framework. So what I mean by that is if I had, let's do another multiplying one quick. If I had, let's say, a -6 times 10 to the 3rd, and I had a positive 2 times 10 to the -8th. All right, I'm just multiplying, so I'm kind of multiplying like terms in a way. So I end up with a -12, because a -6 times 2 would give me -12, times 10 to the, I've got a common base of 10. So I'm going to keep that common base. And I'm going to add the exponents. So 3 plus -8 would give me -5. So you'll notice here, here's the problem. I've got a -12. This has to be between 1 and 10, and it's not. So in this case, I need to convert this. What that means is I want my answer to be -1.2. I want to move that decimal to the left once. If you move to the left, that means you're going to add on the exponent. So I'm going to keep the 10, of course. We're going to keep that base of 10. But if I go left 1, I'm going to add 1 to the exponent. So -5 plus 1 gets me to times 10 to the -4th. Okay, so when you end up with an answer, a number out front that is not between 1 and 10, you have to do one more step of converting to make sure it's between 1 and 10. Okay, so be very careful with that. All right, let's take a look at adding and subtracting with scientific notation. If you have the same exponent, that makes these so much easier. So we're going to take a look at easy ones, but if they don't have the same exponent, that makes it tough. So we're also going to look at some of those. So an easy example would be if I have 3 times 10 to the 3rd, and I'm adding on a 4 times 10 to the 3rd. Because I have these like exponents, I literally treat them like a like variable. I almost just bring it down. So I've got a common 10 to the 3rd, and then all I need to do is to add the numbers out front, very literally. So I've got a 7. So this gives me 7 times 10 to the third. So really easy with those like exponents. Let's look at subtraction as well. So let's say I have 5 times 10 to the negative fifth, and I'm subtracting 7 times 10 to the negative fifth. So far, pretty easy. They have the same exponents. So I'm going to keep that times 10 to the negative fifth, but I'm going to subtract. I'm going to have 5 minus 7, which leaves me with a negative 2. Quickly double check. 2 is between 1 and 10, so that's good. And 7 is also between 1 and 10, so that's good as well. All right, let's take a look at ones where you do not have a like exponent. So when the exponents are different, that means you're going to have to show more work. So make sure you take your time with these. Let's do an example of adding. So let's say I have a 2.4 times 10 to the fifth, and I'm going to try to add on a 3.2 times 10 to the third. Okay, first thing I notice, I don't have like exponents. So first I need to make them like exponents. So I'm going to start off by deciding which exponent I want. So let's say I want to keep the 5. All right, that means I'm going to keep the first scientific notation as is. Now the second one, if I want to make this a 5, then I have to do a little bit of work. If I increase the exponent, that means I go to the left with my decimal. I added 2, so I'm going to go left 2. So I end up with 0.032 as my new number out front. Okay? So again, if you go to the left, you increase the numbers. If you increase the numbers, you go to the left. So you sort of have to remember that. So if you were to come up with maybe like a little cheat sheet, okay, maybe you could say with a visual, if you go to the left, you add onto the exponent. If you go to the right, you subtract from the exponent. Does that make sense? All right, let's keep going. Let's keep adding. So now I have like exponents. So I'm just going to bring that like exponent down. And now I can just add these numbers as they are. So if I add those together, I would end up with 2.432. That number is good to go because it's between 1 and 10. Let's take a look at one more example. Let's do a subtracting one. So this time, let's say I have negative exponents. So let's say I have negative 3. And let's say I have an exponent of negative, let's do a 7. All right, and then my numbers, I'm going to have a 9.98, and I'm going to try to subtract a 6. All right, so first things first, not good, I don't have like exponents. So first thing I need to do is to make them like exponents. So I'm going to decide which one to keep. I'm going to keep the negative 3, just because this number is a little more messy. I'm going to leave that 9.98 times 10 to the negative third, which means I want to make this number to the negative third. So look what I did. I went from negative 7 to negative 3. So I actually added 4. I added 4. If I add 4, that means I go to the left 4. So here's my decimal currently. I'm going to go 1, 2, 3, 4, which means I fill in those loop-de-loops with zeros, and my new value is going to be 0.0006. Okay, so these numbers are equal to each other. All right, so when you add on, you go to the left. Now I've got like exponents, and that's what I needed. So now I can actually do the math behind it. Keep that common exponent, and now I'm going to add my values, or excuse me, subtract, because this is a subtraction problem. So I'm going to do a little bit of work here. If I have 9.98 and I'm going to subtract 0.0006, you would use your calculator for that one. If you were going to line it up and do longhand, you're going to need some more zeros here. So this would be 0.0006. I'm subtracting. I need this to be a 10, which make that a 9, which make that a 7. 4, 9, 7, 9, 9. Does that look right? You guys might have to check my math on that one. I use my calculator too. So there we go. That number is still between, it's still between 1 and 10. So we're okay there. All right, so there's my final answer. So definitely take some time to work with those that do not have like exponents. If you need any extra help on these, definitely check out YouTube. So look up adding and subtracting, scientific notation. You can definitely find some great resources out there. All right, let's move on to exponential functions. First of all, let's talk about what each of these terms mean. These are in your notes, as always. You can get the notes off of Google Classroom as well. A is always your initial amount. That's why I like to use A, initial amount, A. B is always your factor, and it's going to be growth or decay. X is always your time. So what kind of time are we dealing with? So I'm going to give you an example, and I'm going to ask you to do some solving so you can graph it by hand. So for example, let's say I gave you y equals, and let's do 2 parentheses, let's do 1/2 to the x power. So first of all, we got to decide growth or decay. This one is decay. It is decay because 1/2 is between 0 and 1. So when b is between 0 and 1, it's decay, which means, just a little hint here, not on this one, but if b is greater than 1, that's when it's growth. Okay, that's the difference. So this one's decay. My decay factor is 1/2, and my initial amount is going to be 2. All right, let's say we're going to graph this. I'm going to give you these values to plug in for x. I am going to ask for your work on the test. So we're going to take this function, and wherever there's an x, I'm going to put the exponent. So you could start off by just writing all of that out first. Sometimes that's an easier option. All right, now we have to remember all those exponent rules. That's why we learn these. So first of all, we've got power of a quotient, which means I'm going to distribute that -2 onto both sides. They are negatives, which means I flip to the other side. I'm going to kick the 2 up to the top, and I'm going to kick the 1 to the bottom. So 2 squared gives me 4. 1 squared is 1. 2 times 4 gives me a final answer of 8. Let's try that again. Keep the 2 out front. Distribute the -1. 1 to the -1 and 2 to the -1. Kick them both to the other side. So now 2 to the 1's on top. 1 to the 1 is on bottom. Well, anything to the first power is itself. So in the end, I actually end up with 2 times 2, which gives me 4. Let's say 1/2 to the 0 power, there's a special rule there. This is all to the 0 power, so all of that becomes just 1. And 2 times 1 is 2. Oops, I didn't write my exponents right there. So this should be 2, this should be 1. All right, let's distribute first. So I've got 1 to the 1 over 2 to the 1, which stays. Anything to the first power is itself, so I end up with 2 times 1/2. Well, 1/2 of 2 is 1. All right, let's distribute again. Notice the pattern here. We keep distributing that x value each time as an exponent. So I have 1 squared over 2 squared. Got a little bit of work here. 1 squared is 1. 2 squared is 4. So we have 2 times a fourth. Well, let's put that 2 over 1. When we multiply fractions, we multiply straight across, which is 2/4, which reduces down to 1/2. Okay. Here's the shortcut, you guys. Don't forget this. This makes it so much easier to look at. My factor is a half. If I start with 8, that means I times by a half. I times by a half. I times by a half. And I times by a half. That's what the factor does. We times each value by half to get to the next answer. So look out for those patterns. Then when you graph it, we're going to graph our x and y coordinates. So at -2, I'm at 8. 1, 2, 3, 4, 5, 6, 7, 8. At -1, I'm at 4. At 0, I'm at 2, which makes sense because that was my initial value. At 1, I'm at 1. And I'm at 2, I'm at a half. Remember, I need arrows on the ends. I need that nice curve of exponential decay. And do not cross the x-axis. We don't want any negative values. So again, we've got notes and extra worksheets that we did posted on Google Classroom if you need some more support. Let's talk about exponential growth. So again, we know if the value inside the parentheses, if b is between 0 and 1, that's when it's decay. And if it's greater than 1, that's when it's growth. So if I'm dealing with values that I need to plug in, like a real-world problem, then we've got a special growth formula. We have to account for that initial 100%, then add on our b factor and take it to the x. So growth word problems, you need to include that 100% or that 1. So for example, if I had a population, let's say, that was 250,000, that would be my initial amount. And let's say it's growing by 3.2%, that would be my b value. And I want to know how much the population grew in 10 years. So that would mean 10 would be my x value. So if I plug those numbers in, I create an equation, and I'm going to plug that expression into the calculator. So 1 plus, but be careful right here. We've got 3.2%. So 3.2% needs to be written as a decimal. So that means I take this decimal and I move it to the left 2. So that means I'm actually adding on 0.032. If you need extra help with converting percents to decimals, again, YouTube it. Look up percent to decimal. All right, now once you do that, you guys, it's just a calculator problem. So I'm not going to calculate this, but I'll show you how to type it in. You would have 250,000. You actually don't need the comma in the calculator. Parenthesis 1 plus 0.032, close parenthesis, caret top in your calculator to the 10th, and then press the equal sign. Now this is growth, so that means it better be bigger than 250,000 in the end. So keep an eye out for what your new answer is and decide, does that make sense? All right, let's take a look at exponential decay. Decay, only one thing changed. Do you remember? Now one thing that changed is that you're going to have 1 minus your b value. So if I'm talking about, let's say, the rapid decay of some Tylenol that I took, let's say I started off with 600 milligrams of some type of Tylenol, and it decreases at a rate of, let's say, 20% per hour. And I want to know what's left after 4 hours. Okay, so I would label, this becomes my A, this is my B, this is my X. I have an initial value of 600 milligrams. I've got 1 minus 0.20, convert that to a decimal. I'm wondering what I have left after 4 hours. Okay, Now, enter that into your calculator. The one thing I forgot to mention on the previous slide is to make sure to label your answers. So whatever you get here, you need to tell me that the answer is in milligrams, okay? Everything should have a label if it comes from a textual problem. All right, so I know that was quite the video, but I really wanted to cram the whole chapter into here as a good review. If you need extra help, you got so many options. You know, you could YouTube extra help. You could study with a friend. You could take advantage of the Sabre Center, which is something unique to our school, so take advantage of it. If you want to look at my schedule, you could see if you could meet with me. Find a time that works for both of us. All right. Anything else you can think of, you know, study your notes, study on the notes on Google Classroom, okay, rework examples. Whoops, getting sloppy there. Rework examples. That way you know what the answers are. You can check your work. So many options. And you know what, just for fun today, if by chance you watched this whole video, did you watch it all? If you watched it all, the first 3 students that come to me and tell me they watched it all, and I'm going to ask for some details so you can prove to me that you watched it all. The first 3 students that come to me and tell me they watched the video, you might get a little something. Let's see what we can come up with. All right? Don't tell your friends. You want to be the first one. So come find me. Study hard. Test Tuesday. Good luck. Let me know if you need anything.